Quality Control and Improvement, Module 2, Lecture 2. Learning objectives for Lecture 2 are to explain the concepts of population, sample, random variable, and probability distribution. Compute the sample mean, variance, standard deviation of a probability distribution. Calculate probabilities from probability distributions. Select an appropriate probability distribution for use in specific applications. Reading assignment is Chapter 3, pages 65 to 96. The first thing to understand is the difference between a population and a sample. So let's say we're manufacturing transmissions, and on a given day we manufacture 1,000 transmissions. The 1,000 transmissions would be our entire populations. Let's say we take a representative sample of 10 of those transmissions and inspect them. So the 10 that we select, that is our sample for that particular day. So that leads to the definition of a population and a sample. A population is the entire collection of objects or outcome about which data are collected. That would be our 1,000 transmissions. A sample is a subset of the population containing the observed objects or the outcomes and the resulting data. So that would be the 10 that we select out to test and do measurements on. If we select a sample from a population to make a measurement, the measurement is usually denoted by a variable, such as x. A variable whose measured value can change is referred to as a random variable. For example, x might denote the length of a sample of boats taken from a manufacturing process. X could take on any value, theoretically. To obtain further information, we can use statistical methods to analyze data and determine the performance of the underlying manufacturing process. Often the underlying process we're sampling can be modeled by probability distribution. A probability distribution is a mathematical model that relates the value of a measured variable with the probability of occurrence of that variable in the population. There are two kinds of probability distributions: continuous distributions and discrete distributions. When the variable being measured is expressed on a continuous scale, can take any value, its probability distribution is called a continuous distribution. On the other hand, discrete distributions can take only discrete values. This is a good chart I like to use to remember the difference between the two. So on the left plot, this is what's known as a discrete probability, or sometimes called a probability mass function. Notice, so here we have the random variable x1, x2, x3. These are our samples we take. So x1 has a probability of p of x1. This is a function. This probability is a function of the random variable. So here, notice it can't take on any value. It takes on specific values. On the other hand, on the right is what's known as a continuous probability distribution function, often just shortened to probability density function. So this is a continuous case. It's a function. At any point on the x-axis, there is a specific f value. So here, to obtain the probability, we can only talk about a probability over an interval. So for example, the probability of x being between a and b is given by this integral from a to b, f of x dx. Now fortunately, we can use Minitab to do all this work for us. So we don't have to do actually integrals. Minitab will do all the hard work for us in this class. So let's talk about specific distributions, both discrete and continuous, that we're going to use in the class. Now the textbook covers a lot of different examples, but a lot of them that the book covers aren't really that useful or very restricted. So we're going to focus on the ones that are most useful in this particular class. The first one to talk about is a discrete probability distribution function known as the binomial distribution. So let's take a look at how this comes up. So consider the following random experiments and random variables. Let's say we flip a fair coin 10 times. We let x be the number of heads produced. So x here is our random variable. Let's look at a different case. So a worn machine tool produces 1% defective parts. Let's let x be the number of defective parts in the next 25 parts produced.
A multiple choice test contains 10 questions, each with 4 choices, and you guess at each question. Let X be the number of questions answered correctly. So these are all examples of where a binomial distribution would be appropriate to use. Because this is a random experiment or a sample with only 2 outcomes. It's either success or fail. Either the coin is either heads or tails. Either the parts are either defective or they're not defective. Either the question you either got right or you got wrong. So they only have 2 outcomes. So a trial with only 2 possible outcomes is called the Bernoulli trial, and we can use the binomial distribution to describe it. So formally, the binomial distribution is defined by the following function. Here, P is the probability. The probability is going to be between 0 and 1. If the probability of 0, well, then it doesn't occur. If the probability is 1, then it always occurs. For a lot of our cases, obviously like flipping a coin, if we flip one coin one time, we know there's a 50% chance we get a heads, 50% chance we get a tail. So in that case, P would be 1. But if you perform that experiment over and over and over, what's the probability of getting 3 heads in a row? Well, it's not 50%. So this is where the binomial distribution comes in on how to calculate that. N is the number of trials that we make, the number of attempts, you might say. So in this probability distribution function, again, Minitab will calculate this for us. We don't actually have to plug this in and do this, fortunately. P is the probability, N is the number of trials, X is the success on any given trial, mu is the mean, and sigma here is the variance, or sigma squared is the variance.
So on page 82 of the textbook, he talks about an example. He says, using the binomial distribution. So he says, use the binomial distribution to calculate the probability of obtaining X non-conforming items if P is equal to 0.1 and N is equal to 15. So what I've done is I've done this in Minitab. He does it calculating it using the formula. So first thing to do is enter the data in the table. So if you start Minitab and enter the first column, so right below C1, just put data, and then type 0 through 15. I'm only showing 0 through 10 here, but I just clipped the part of the table. Then go to Calc, Probability Distribution, and select Binomial. And once you do that, it'll come up with this window. So select the probability, select the number of trials as 15, and select the Viet probability. In their input column, again, this would typically be blank, and you can select it, and then you'll fill it in here with the data column shown here. When you click OK, what will print out is this little probability distribution function with the results plugged in. So here, the probability of 2 is 0.266, so about 27%. The probability of 4 would be about 4.28%, etc. So this would be the probability, for example, of getting 4 non-conforming items would be 4.3%. You can quickly see as getting up to 10, it gets to be about 0. So there's really no need of going from 11 to 15. Next distribution we'll talk about is what's known as the Poisson distribution. The Poisson distribution is often used in quality control, reliability studies, and insurance. The Poisson distribution is often useful in estimating the number of occurrences of an event over a specified interval of time or space. A typical application of the Poisson distribution in quality control is as a model of the number of defects or nonconformities that occur in a unit of product. Any random phenomena that occurs on a per unit basis, for example, per unit area, per unit volume, per unit time, is often well approximated by the Poisson distribution. Formally, the Poisson distribution is given by this formula, where the parameter lambda is greater than 0. The mean and variance of the Poisson distribution are as follows.
the mean is equal to lambda, and the variance is equal to lambda. So the example on page 84 in the textbook, he calculates this example using the function. So suppose that a number of wire bonding defects per unit that occur in a semiconductor device is a Poisson distributed with lambda equal to 4. Then the probability that the randomly selected semiconductor device will contain 2 or fewer wire bonding defects is given by the following calculation. So here x is less than or equal to 2, so the sum goes from x equals 0 to x equal 2 of the sum. So here x would be 0. You would do this calculation, then plug in x. This is the value when x is 0. Same thing when x is equal to 1, you get this number. And then finally, when x is equal to 2, you get this number here. So add it all together, you get 0.238, about 23.8%. Of course, Minitab will do this calculation for us. What I did is I went into the Minitab and I calculated, again, the first column with the data, 0 through 4. If you go to Calc, probability distribution, Poisson, it brings up the slide here. You can enter the mean, which you tell us that's the lambda value, 4. And you input the input column, which is my data. Click OK, and you get the following value. So here, so this is when x is 0, x is 1, x is 2. So he wanted to know when it'll contain 2 or fewer. So we're going to have to add up the case when it's 0, 1, and 2 to actually get the numbers we got in the previous slide. But you can see Minitab makes these calculations for you. Finally, the normal distribution. The normal distribution is probably the most important distribution in both the theory and application of statistics. The normal distribution has been used widely in a number of practical applications in which the random variables are heights and weights of people, test scores, scientific measurements, amounts of rainfall, and other similar values. It's also widely used in business applications to describe uncertain quantities such as demand for products, rate of return for stocks and bonds, and the time it takes to manufacture a part or complete many types of service-oriented activities. Formally, the normal distribution is defined by the following complicated function. Mu here again is the mean, and sigma is the standard deviation. Sigma squared being the variance. So the mean can obviously be between minus infinity and infinity. The standard deviation has to be greater than 0. The normal distribution is used so much that we frequently employ a special notation given by the following. N is a function of mu and sigma squared. This is to imply that x is normally distributed with a mean mu and variance sigma squared. The visual appearance of the normal distribution is symmetric or bell-shaped. So here it's clustered about the mean with equal space on both sides. Sigma squared describes how much it's spread out from the mean. So here it's important things to note about the normal distribution, that 68%, roughly 68.26% of the population falls between the limits defined by plus or minus 1 sigma. 95.46% fall between plus or minus 2 sigma, and 99.73 fall between plus or minus 3 sigma. Let's look at example 3.7 from the textbook using Minitab. The time to resolve customer complaints is a critical quality characteristic for many organizations. Suppose this time in a financial organization is normally distributed with mean 40 and variance 2 squared. What's the probability that a customer complaint will be resolved in less than 35 hours? So here what we're asking is, what's the probability of x is less than or equal to 35, where x is our random variable, represents the number of hours. So here we go to launch Minitab, go to Calc, probability distribution, select normal. You'll get this window that'll pop up. So here we want to put the cumulative probability. We want to select, enter the mean, enter the standard deviation. Remember, 2 squared is the variance, so the 2 is the standard deviation. Input constant, we want to enter 35. That's what we're interested in.
So when you click OK, Minitab will give you the answer. So if X is 35, it's roughly 0.00062. Let's do another one from the textbook, example 3.8. So here we have the diameter of a metal shaft used in a disk drive unit is normally distributed with mean 0.2508 inches and standard deviation 0.0005 inches. The specification of the shaft has been established as 0.2500 plus or minus 0.0015 inches. What fraction of the shaft produced conform to specifications? So one thing I found useful is that when you do these kinds of problems, it's very useful to plot out what the normal curve looks like and list the information that's given. So here we're told that it's normally distributed with mean 2.2508. So I would draw my normal curve. I put 0.2508 right on the mean, and I list the information on the standard deviation that we're told. Now, this upper and lower specification, he tells us what that is. He says it's 0.2500 plus or minus 0.0015. So if you go minus 0.0015, you get to 0.2485. And if you go 0.2508 plus 0.0015, you get to 0.2515. So what we're asking is we want to calculate the probability of this shaded blue region. So when you do that in either by hand or in Minitab, you really have to do this twice. What we're asking is you want to find the probability that X is greater than 0.2485 and less than 0.2515. So the way to do that is to first calculate the probability that X is less than 0.2515. So that would be all the region. And subtract from that the probability that X is less than 0.2485, which would be the region to the left of 0.2485, the lower specification. So when you subtract these two numbers, what you'll get is you'll get what's left in the blue region. So if you do this in Minitab, just like we did before, if you calculate this one, you'll get 0.9192, and if you calculate this one, you'll get 0. I think it's out here in the fifth or sixth decimal place, but we're only going to keep 4 significant figures here, so it's 0. So our value is 0.9192, about 92%. So thus we expect the process yield to be approximately 91.92%. So in other words, about 91.92% of the shafts produced will conform to specifications.
So given we have some data either from a experiment or data collected from a sample that we've taken from a population, how do we know whether a particular probability distribution is a reasonable model for the data? One method we can do is to use what's known as a probability plot to see if the data sort of line up with a theoretical distribution. This is really a subjective visual examination of the data, but Minitab makes it easy to do this. So let's look at example 3.13 of the textbook. He gives some observations on the road octane number of 10 gasoline blends, and he shows them as the following data. Here we hypothesize that the octane number is adequately modeled by normal distribution. Is this a reasonable assumption, he asked. So one thing you can do, so you can, doing this without Minitab would be rather difficult. You'd have to get some graph paper, plot this, and that sort of thing. But, Minitab, you fire up Minitab, you type in your data in the first column here. And I've called it data. Go to graph, probability plot, select single, click on the distribution, and select normal. So here, when you do this number 2, it'll pull up this this little window. If you click on distribution, you can select normal distribution. There's a bunch of them you can select, but we're kind of interested in the normal one because that's what he's asked us here. So select normal, then click OK. Then when you do that, you get the following plot. So here it shows the data in blue. The center red line shows what they would be if they were normal. So a normal distribution would, if this data were normal, it'd fall exactly on this red line, the center red line. This lower red line and the upper red line is sort of what's known as the 95% probability index. This is a sort of a confidence interval. So this kind of gives you a good feeling that this data more than likely are following a normal distribution, because one, they're all falling sort of on the line. I mean, there's a couple of outliers, but in general they're falling on the line. And also they're falling within this 95% confidence interval. Also, another thing is what's known as the p-value. We'll talk about the p-value in the next chapter, but it pops up here as 0.654. So anything above 0.05 is significant, and this leads us to conclude that the octane number is probably more normal than not. I mean, you can't get a definitive answer from these probability plots, but you can sort of get a good feeling that yes, your data are falling along the normal line.